So solving for the values of alpha and omega naught, we have alpha equivalent to R over 2L equal to 8 kilorad per second. Then we have omega naught equivalent to 1 over square root of LC is equal to 10 kilorad per second. Now our alpha is less than omega naught, so our circuit is underdamped. Solving for omega d is equivalent to 6 farad per second. We have our S1 and S2 equal to negative 8K plus minus J 6K. Now solving for the complete response, we have I of t equal to IF plus IN. For the forced response plus the natural response. So for the forced response, for IF, our circuit is in a steady state. So our capacitor is an open circuit and our inductor is a short circuit. So if this is open, our IF is just equal to 0 ampere, and if our current is 0, so the voltage across the capacitor is equivalent to the voltage 100 volts. So Vc of F equals to 100 volts. Now for the natural response, since this is underdamped, we have Ae to the negative 8 kT cosine of 6 kT plus Be to the negative 8 kT sine of 6 kT. So since our force response is 0, this is just equivalent to our complete response. So solving for the values of A and B, so at t equals to 0, we have 0 equals to A plus 0. Our A is equivalent to 0. So solving for the value of B, we will derive this equation. So we just arrive with this equation. And solving for B at t equals to 0. So at t equals to 0, dt of 0 equal to negative alpha plus omega d B. So this is equivalent to 10K equal to, this is 0. Then we have 6KB. Our B is equivalent to 5 over 3. So our complete response for I of t is equivalent to 5 over 3 e to the negative 8 kt sine of 6 kt u of t amperes. So how do you solve for the expression Vc of t? So Vc of t, so we all know that I current across the capacitor. So the current across the capacitor, given the current across the capacitor, the voltage across the capacitor can be solved using this formula. 1 over c integral of I of t dt plus the initial value of v. By integration, we have Vc of t equal to 1 over 2 micro. We have integral of 5 over 3 e to the negative 8 kt sine of 6 kt plus the initial value of VO, which is 100. Now this integral can be solved using integration by parts. Integration by parts, we have uv minus integral of v du. We will assign u as our e to the negative 8 kt. Our du is equivalent to negative 8k e to the negative 8 kt dt. And we have our dv equivalent to sine 6 kt dt. So our v equivalent to negative 1 over 6k cosine of 6k t. So we have 5 over 3. Now this integral can be solved using, again, integration by parts. We have u equal to e to the negative 8 kt du equivalent to negative 8k e to the 8k t dt. And we have dv as cosine of 6 kt dt, where v is equivalent to sine of 6 kt. This equation becomes 5 over 3 . Since we are going back to this form, we can equate this equation. We have our e to the, this equation, e to the negative 8k t sine of 6 kt is equivalent to this. Transposing this to the other side, so we have 25 over 9, solving for e to the negative 8 kt sine of 6 kt. We have, so our vc of t is equivalent to 1 over 2 micro times 5 over 3 times this equation. Our vc of t is just equivalent to negative 50 e to the 8 kt cosine of 6 kt minus 100 over 3 e to the 8 kt sine of 6 kt plus 100 u of t. We can solve this using the forced response plus the natural response. We have Vc of t equal to 100 plus Ae to negative 8 kt cosine of 6 kt plus Ve to the negative 8 kt sine of 6 kt. Solving for the values of A and B, so at t equals to 0, we have 50 equal to 100 plus A plus 0. So our A is equivalent to negative 50. Now, solving for the value of B, we have at t equal to 0, or dvc dt at 0 equal to 0 equal to negative alpha A plus WD B. Solving for the value of B, we have equal to negative 200 over 3. So finally, our complete response is plus 100 U of T volts.